So, some mathematical essentials before going into this course. We should know about the cross product of vectors. So, we all know vectors from physics and other courses. Um, when we're talking about two vectors named A and B, when you do a cross product of these two vectors A and B, you will get a result in terms of a vector C. So the cross product of vectors is applied on two vectors, and the result would be a vector itself, which we call it vector C here. So how you show this operation, you have A cross sign, that's the cross product meaning. Um, A vector cross B vector, that would be equal to C vector. So that uh, is a symbol of the cross product. So this cross product would give a vector C. This vector has a magnitude. The magnitude of that vector would be A times B times sine of theta, where A without R, without that basically vector sign, means the magnitude of the vector. So every vector, as you know, has, when you're talking about the vector, that vector has a magnitude. So that is the magnitude of that vector. So this is, for example, vector A. A without that vector sign would be the magnitude of that. And then the vector has a direction. That direction is usually shown through some basically angle. So if you have a system of coordinates, for example, let's say this is my system of coordinates on two dimensions, x and y, then this direction of that vector is shown through an angle of theta, which is between basically this x vector or x axis, that's the horizontal vector, and the vector itself. So that's theta is showing kind of the direction of that. So my vector C would have a magnitude of A times the magnitude of A times magnitude of B times sine of theta, where that theta is the angle between A and B. And what about the direction? The direction of the vector will be perpendicular to both A and B. So this is shown by the right hand rule. So if you're using basically your index finger of your right hand in the direction of vector A and your middle finger in of the right hand in the direction of vector B, and you're considering the theta angle between these two, then your thumb should show the direction of vector C. So this is the right hand rule, which is used to explain the cross product of two vectors. Okay. All right. So this is from the cross product. How do we do that in MATLAB? So in general, if you're having two three-dimensional vectors, so what I showed here uh, was a two-dimensional vector. But in general, if you have a three-dimensional vector with respect to x, y, and z axis, so for example, this specific vector of A, which is a three-dimensional vector, and if these are the coordinates, ax, ay, and az, bx, by, and bz for the two vectors. So what does ax mean? So the projection of A over x-axis would give you this vector, which you call it ax, right? And the projection of the same vector over the y-axis would give you an ay. So same thing for the three-dimensional vectors. Let's call these vectors I, j, and k. I, j, and k. So if you have your ax times vector I plus ay times vector j plus az times vector k, you should be able to find out your total A vector. And now let's go to MATLAB. How do you do that in MATLAB? So I'm bringing MATLAB screen here. So if you have A equal to, for example, minus 1, 2, 3, okay, and then B, let's say, is 6 minus 5 minus 8. So these are your two vectors. And then if you want to get the cross product of these two, you can use the cross of A and B as a command. Cross A and B. This gives you another vector. So this means that your C vector would have the component on the x-axis equal to 4, the component of 8 on y-axis, and the component of -2 on the z-axis. And then we have another type of product on vectors, which we call it the dot product. And that dot product is basically giving out a scalar, not a vector. So the result of the dot product of two vectors, A and B, would be a scalar, not a vector. Would be a scalar of C without that vector sign on that C, because it's a scalar. And we show the dot product using a dot sign, as you can see. And the dot sign is a symbol. And the magnitude of that scalar would be A times B times cosine of theta, where, again, theta is the angle between A and B. So the result of a dot product would be a scalar. And if you want to do the dot product in MATLAB, you can use the dot command. So for the same two vectors, the dot of A and B, as you can see, becomes a scalar of basically -54, which if you do basically the same operation, magnitude of A times magnitude of B, and if you find the angle between those two vectors, call it theta, and find that cosine of theta, that would give you the same result as what you got here in MATLAB. Now let's go to some physical principles. So first and foremost, we need to understand what magnetic fields are. First of all, a magnetic field is a vector field. It means it consists of, or we can imagine that field of a bunch of vectors. Vectors are those types of quantities that have both magnitude and direction and an angle. So this type of vector inherently exists around a permanent magnet. So if you have a permanent magnet, also permanent magnets, they have two basically poles N and S. This permanent magnet does produce basically a vector field around it. Alternatively, you can create that magnetic field by an electric current which flows inside a conductor. So if you have a conductor in which a current is flowing in a certain direction, then there would be some magnetic field existing around that conductor as well. Okay, so as you can see, the direction of the vectors in the magnetic field are such that they start from the North Pole and go towards the south. So starts from the north, go to south. So starts from the north and then comes back to the south, as you can see. So this is the vector field around permanent magnet. Now here are a few definitions that are important associated with these magnetic fields. So what was magnetic field was a vector field which exists around the permanent magnet, or can be produced by an electric current flowing inside a conductor. That produces a magnetic field. So in a permanent magnet, those basically magnetic field vectors start from pole N, go towards pole S. And here are a few definitions associated with magnetic fields. The first is magnetic, what we call magnetic field intensity. So magnetic field intensity, which is a vector, usually shown by H sign. So H with a vector sign above it. It has a SI unit. What does SI stand for? System of International Standards. SI is Standard International. The SI unit of magnetic field is A over M, where A is ampere. So amperes per meter. This quantity is an indicator of the strongness of the magnetic field. So the bigger A over M is, or amperes per meter is, it means that it's a stronger, we do have a stronger magnetic field. So this is magnetic field intensity. The unit is A over M, shown by H with a vector sign above. There is another definition, which we call it magnetic flux. This magnetic flux is a scalar quantity. So this is not a vector. It's a scalar quantity, which we usually show it by the phi sign. It provides a measure for the flow of magnetic field through a specific area. So if you have an area like this, for example, consider a portion of the area on a sphere, for example, then magnetic field, or sorry, magnetic flux is showing, magnetic flux is showing how much basically, how how much magnetic field is passing through that specific surface. So if phi is big, means that through that specific area, more magnetic field is passing. A more intense magnetic field exists, which is passing through that specific area. That makes sense. So then let's go to magnetic field intensity, magnetic flux. This one is a scalar. Magnetic field intensity is a vector. And then, so the SI unit for magnetic flux is Weber, is called Weber. And then we have the magnetic flux density. So don't confuse it with magnetic field intensity. Magnetic field intensity is H. Magnetic flux density is B, is a vector. There is a certain relationship between B and H through something that we call it mu. So the magnetic flux density and magnetic field intensity are related through what we call magnetic permeability, or mu. Okay, so that mu is what relates B to H, and the unit, the SI unit for magnetic flux density would be Weber over meters squared, or Tesla. So Tesla is equal to Weber over meters squared. Another name for Weber over meters squared is Tesla. Okay, so we talked about magnetic field intensity, magnetic flux density. The relationship between magnetic flux density and magnetic field intensity is through what we call mu, which is the permeability. That permeability is basically has a unit itself. Its SI unit is Henry per meter. And this mu is showing the property of the magnetic material. So if you are in the open air, the permeability of the open air would be mu, what we call mu zero. If the magnetic field is existing inside a magnetic material, for example, iron, then depending on the material of that magnetic material, we could have what we call a permeability coefficient of mu r, which is getting multiplied by mu zero to show the total permeability of that magnetic material. So magnetic permeability of a material is called mu, which is the product of mu r, which is the permeability coefficient times mu zero. What is mu zero? Mu zero is permeability of air. So if we want to basically have an idea of how much that mu r could be for strong magnetic materials, mu r could be in around basically a few thousand times mu zero, which means that when magnetic fields are basically going through an area, if that area contains open air versus certain magnetic materials, then the amount of magnetic field that goes through that magnetic material is much, much more than the magnetic field that goes through the open air. By how does it show? By mu r. How much could mu r be? In the amount of few thousand. So magnetic fields are more likely to go through the magnetic material a few thousands more, or stronger a few thousand more than inside the open air when there is a magnetic field existing in some area. If that makes sense. So for the open air, mu r is equal to 1. For magnetic materials is in the order of several thousand. Now, in order to understand how a magnetic field can be produced through an electric circuit or electric current, we have a law that is called the Ampere's law. This law is showing us how an electric current can produce a magnetic field. And that shows the relationship between the magnetic field intensity and the current that exists in a certain electric circuit. So consider a conductor like this without any known, consider a very strange shape for that conductor. It doesn't have to be straight. Okay? It could be like a wire that you just bent it over a few times, but there is a current of Inet flowing through this wire. So this has to be a closed circuit, obviously. When there is an electric current, there has to be a closed loop, right? But we're showing portion of that electric circuit where it contains that current. Now, around that conductor in that certain area, there will exist a magnetic field that can be basically shown by its magnetic field intensity, or H. Now, by Ampere's law, there is a certain relationship between that current that is existing in that conductor and that magnetic field intensity through a line integral. So what does that line integral mean? It means that if you assume an arbitrary closed path around that conductor, this is an arbitrary closed path. It doesn't have to have a certain shape. It doesn't have to be a circle. It could be any shape that you want. Okay. Now, since we're saying that this iNet is producing a magnetic field, then at each point on that closed path, there should be a certain magnetic field and a certain magnetic field intensity of H. So at this point, I'm showing those magnetic field intensities by these red vectors at each point on this path. So for example, at this point, this is my magnetic field in this direction. For example, at this point, it could be in this direction. At this point, could be in this direction, and so on and so forth. We just don't know because this is an arbitrary closed path. But we do know that there is a certain magnetic field intensity. So if you assume that you have all of these magnetic field intensities, if you have a way of measuring them at each certain point on this closed path, we call that H at that specific point. And then if you're having basically certain DLs in the direction of that closed path at that certain point. These DL are the differential elements of length. What it means is that they are basically pointing in the direction of that closed path. And as you move through your closed path, the direction of these DL elements would also change depending on how you are shaping that closed path there. So this is my wire. This is the path around that wire. This is the current that goes through that wire. And on this path, these are basically DL elements that are tangential to the path. And here are basically my H values at that certain point, which we don't know. It may be tangential. It may be basically in another direction. That's not the point in here. The point is that if you are able to measure those H's at each point, and if you're having those DL elements, if you just go ahead and divide this path into small enough sections and do these calculations of H times DLs. And then if you go ahead and make these segments smaller and smaller and smaller, that becomes integral, right? Since you are basically finding these H times DL plus H times DL plus H times DL over this closed path, that integral would be a closed integral. If you go ahead and add all of these elements together, that becomes Inet, the current that is existing inside this closed path in that conductor. So this is quite basically an arbitrary path. It doesn't have to have any special shape. But for certain geometries, you would find that this law can be very useful in terms of determining how much magnetic field intensity you have around the conductor. So for our special case of a conductor that is right without any bending, and we should have these H's in these closed paths around that are in the form of circles. So at each point, these are concentric circles around basically this conductor. At each of these circles, at each point, we should have the same amount of magnetic field intensity, because the way that these concentric circles are around these conductors is in a way that they have the same distance from that conductor. So H must be the same. But the direction of H should be all the time tangential, which means that this would be a 90 degree, this would be a 90 degree with respect to basically that radius that comes from the center of that circle and joins that point. So if you go ahead and do this math, this is an inner product or dot product, as you can see. So what is the dot product? The dot product of vectors means that you must basically find a scalar. That's why basically this integral's outcome would be a scalar, Inet. The current is a scalar. Basically, the instantaneous current is a scalar quantity. So that's because we're doing the dot product. So we do the dot products and then cosine of the theta. What is theta? So this is your circle at this certain point. This is your H. This is your DL, right? So they are in parallel. So the angle between them is 0. That's why H times DL must equal to H times dl, the magnitude's cosine of 0, which is 1. So that becomes h times dl. And when you do the integration, basically over that closed path, which is the perimeter, the perimeter of that circle, that gives you the total current, which is I, right? So H can be found, the magnitude of H, or magnetic field intensity, would be I divided by 2 pi r. So this is coming directly from this Ampere's law. So we covered this Ampere's law, which is using a closed path and a line integral, the H times dl products all together, added together, that is the definition of integral. Over a closed path, they will give you the total current that is within that conductor. The curved right-hand rule gives you basically the direction of the magnetic field. So based on that, you're having a straight conductor like this. If you are putting the thumb of your right hand in the direction of the current, then your 4 other fingers would point to the direction of the magnetic field. So that's how you can find out these concentric, basically, circles around this right conductor. On each of these circles, the magnitude of that magnetic field intensity would be the same, equal. As we go away from the conductor, based on this relationship, since R becomes bigger, H becomes smaller. So the strongest field is very close, right attached to the conductor itself. That's where we have the strongest magnetic field. As we move away from the magnetic field, then based on this relationship, the magnetic field intensity becomes smaller and smaller. And when we go to infinity, that becomes 0. Okay? So that's basically how we can take advantage of the Ampere's law in order to determine the magnetic field intensity around certain conductor shapes. So this was for the straight conductor. Now, if you have a solenoid, so this is basically a solenoid. Solenoid is showing you a winding of wires that are wrapped around a magnetic core. So this is your magnetic core. You have wires wrapped around on a certain side. Through this Ampere's law, we can basically find the magnetic field intensity of that solenoid to be equal to Ni over L, where N is a number of turns of that solenoid. I is the current flowing through that winding, and L would be the average length of your magnetic core. So if you're considering an average length of that magnetic core to be equal to L, you can see that that would determine how much the magnetic field intensity would be inside that solenoid. If L is bigger, then magnetic field intensity would become smaller. If N is bigger, the number of turns is more, then you would have stronger magnetic field. If current is more, you would have stronger magnetic field. But if L is small, again, you would have a stronger magnetic field. So that shows basically the relationship. Let's go over a recap of what we did for today. I provided some math essentials. We defined the cross product of vectors, which we haven't used so far, but the physical interpretation of that would be in our course. The cross product of vectors would be a vector itself. The magnitude of that vector would be found from AB sine of theta. Then we talked about the dot product of vectors, which would be a scalar, not a vector. And the magnitude of that scalar would be AB times cosine of theta. And we talked about magnetic fields and 3 important definitions for magnetic fields. One is magnetic field intensity, or H, which is a vector. Its SI unit is A over M, amperes per meter. We have magnetic flux density, or B, which its unit is Weber over meters squared. The relationship between B and H is through mu. And mu is basically permeability. That permeability for magnetic materials is very big. For the open air is small. And then we have magnetic flux, which is not a vector quantity. It is a scalar quantity, which kind of shows how much magnetic field is passing through a certain area in the air. And then in order to determine how much magnetic field intensity we have, we use the Ampere's law, which is showing the relationship between the current inside a conductor and the magnetic field that is existing around an arbitrary closed path around that conductor. So using this Ampere's law for certain shapes, for example, this right wire, we could determine how much magnetic field is around, how much magnetic field intensity is around that conductor. And for another geometry, which is a solenoid, we could determine how much magnetic field we have. So there are 2 basically cases where we found the magnetic field intensity.